Hi, I'm Moshrefzahdeh, a PhD candidate at the chair of Geoinformatics and a research associate at Hans-Eisenmann Forum of Technical University of Munich.
And I'm Gackstetter, project engineer and researcher, also at Hans-Eisenmann Forum. In the next 15 minutes, we would like to talk about the challenges that we're facing with respect to information management and integration in the field of agricultural research, and also the concept that we developed to address and tackle these challenges. Currently, we are developing some of these concepts at our institute, which is the Hans-Eisenmann Forum for Agricultural Sciences, short HAF. It is the Central Institute for Agricultural Sciences of Technical University of Munich. The HAF consists of more than 30 members, which are mainly chairs of different disciplines in the field of agricultural science. They focus on different aspects and on various scales, and accordingly the overall data is also very heterogeneous, diverse and scattered across different locations. Bringing together all this data into one integrated system is a key to extending and improving the overall data management of our members' research.
But, David, these requirements are not limited only to the agricultural research environment. In general, the agricultural ecosystem forms a complex system of interacting and changing elements and subsystems where many stakeholders from diverse disciplines are involved. Understanding and working with such a complex system requires a comprehensive description of the whole ecosystem and an approach that enables interoperable and cross-scale management of distributed information resources. And here is where our concept of distributed digital twin plays a critical role. But before I explain our concept and how it works, let me first dig a bit more into the current situation that we are in and the challenges we face. Consider a farmer, a business enterprise, an end product seller, a researcher. They all need to work with a great amount of diverse information and resources almost every day in order to correctly plan their next steps. Each of these stakeholders has different interests and hence different requirements. At the same time, stakeholders provide comprehensive specialized information which are usually scattered over different organizations. The fundamental challenge is therefore to make this information, usually in distributed form, available to actors in a form that meets their needs and to harmonize it across the various stakeholders such that it helps establish a common and cross-scale understanding of the running system. This requires integration of scattered information from distributed sources. To do so, we often face 5 main challenges. The first is lack of transparency. Different stakeholders have different information about the same real-world objects. They typically don't know what data is available from other sources. The second challenge is the data integration in a multidisciplinary and distributed environment. Different stakeholders do not always define and refer to a specific real-world object in the same way. This makes integration of information difficult and causes problems when linking the data of multiple actors. Having solved the first 2 challenges, the next challenge is how these real-world objects should be represented digitally and what level of details do we need to consider. The fourth challenge concerns data harmonization in an interoperable and platform-agnostic way. And last but not least, it is the persistent availability of the historical and real-world information and resources. To handle data in such a complex system, we bring forth the concept of a smart rural area data infrastructure, or in short, SRADI. SRADI is not just a single platform, it is a multidisciplinary information infrastructure which handles various stakeholders, multiple applications, and distributed information resources. Interoperability is an important aspect of SRADI, achieved by using international standards such as the ones from Open Geospatial Consortium. More importantly, SRADI is not a single platform, but rather an infrastructure of various platforms and resources. The SRADI concept consists of 3 main pillars: Actors are persons or legal entities who define the use cases and accordingly the required resources and functionalities, but at the same time they offer and provide their own resources and services. The second pillar is the applications. Applications form the interface layer using which actors evaluate and assess the situation and accordingly make decisions. Applications offer interfaces to access the added value provided by the distributed digital twin that comprises complex simulations, data, and information. A digital twin is defined as a comprehensive physical and functional description of a component, product, or system which includes useful information for all life cycle phases of the physical things. Now, in complex systems where we have scattered information and resources owned or provided by diverse stakeholders, we need to think of a distributed version of the digital twin. The SRADI distributed digital twin itself consists of 4 components. Analytics toolkit, which is in fact a warehouse of existing modeling, analysis, and simulation tools linked to the rest of the SRADI components using standardized service interfaces. Virtual landscape model, a digital spatio-temporal representation of the agricultural environment. Sensors and sensor data comprising all available in situ and remote sensors. This also includes data from third-party providers which are used for enriching the digital twin with real-time information. And the catalog, which is the core component of the distributed digital twin. The catalog plays a critical role for our distributed digital twin as it provides, on one hand, the basis for linking diverse types of resources to each other, and on the other hand, represents the complex interconnections of resources as well as their owners and organizations.
Now, as you learned more about the concept of SRADI, we'd like to show you the implementations that we are about to develop for the research station Stefan, and more specifically for the members of our institute. And let's dive into it, starting with the sensor data infrastructure. Efficient and interoperable data management is an elementary basis for top-level research. Continuous and automated sensor data acquisition, however, by remote access poses certain challenges in the agricultural sector, like high ranges, energy restrictions, and so on. Given that there is not the necessary IT expertise to set up a known sensor data infrastructure, to get data from the sensor to the application, a researcher might spend a lot of time and resources on setting up this self-reliantly, which is actually a barrier to developing the actual innovative research idea that a researcher is pursuing. So basically, to help our researchers with this issue, we wanted and we are about to provide a comprehensive end-to-end data processing service from the sensor to the actual application, which is based on open, free and standardized technologies. This end-to-end chain can be done with different radio transmission technologies. We decided to offer a radio transmission technology which is based on low power wide area networks like LoRaWAN, which is well for a long range availability, low energy consumption regarding also low cost and high data security. Furthermore, we use open source network technology, network server technology from the Things network. Furthermore, our standardized data management is also a key element here. We are using standards from the Open Geospatial Consortium, such as the Sensor Things API. We use open source implementations for this, like the Frost server, and are by that open and capable of interfacing in an interoperable way. Furthermore, we are also offering a sensor management web application, which is basically a very user-friendly web app for managing on a GUI basis sensor data and physical things. When we look at intuitive data visualization, this is also a key element of our sensor data processing infrastructure. Here we, for instance, see here dashboards can be easily configured, can be easily used for quick for a quick view about the current situation of the sensor data. Identity and access management is a very important aspect that we need to deal with, which needs to be secure in order to be used, in order to be reliable for the researchers. So basically we're using here state-of-the-art technologies to secure all the apps and to make sure that only users have access to data which have the corresponding rights. And with this I give now further to Mandana, and she will tell you more about the implementations of our core component of SRADI, about the catalog service.
Thanks, David. Have you ever come across questions such as, how has the crop yield changed in recent years? Which experiments have already been conducted using the method we have in mind? Or what was the microclimate for this crop in the last weeks? To whom does the time series data on precipitation at this location belong? We as researchers spend a lot of our time and energy searching for information and resources which are required for our work. Instead, we should put our effort and time on the main theme of our research, such as testing different approaches or experimenting different methods and so on. This is exactly one of the purposes of our catalog. The catalog of the distributed digital twin covers not only datasets and services, but also all individual physical things. It also covers information about involved organizations and stakeholders and the resources they provide or maintain. For each individual physical object, we can register one entity in the catalog. This has been made possible by assigning a stable identifier to each catalog entity. A comprehensive data model has been introduced upon which our catalog performs. This data model offers two special features. First, information resource types are specialized. This means that our catalog assembles more diverse resources relevant to distributed digital twins of agricultural ecosystem and landscapes, such as online services and applications, datasets, software, projects, method, and also physical things including landscape objects, devices, or even animals. By explicitly defining the type of a resource, we add specific semantic related to the digital twin of the agricultural landscape, which improves the structuring and retrieval of information in the catalog. Another feature is the links between resources. For each resource, we can have either outgoing references, where the owner of the resource can define what other resources it is related to, or incoming references, where owners of other resources can define relationships with this resource. For each of these, regardless of incoming or outgoing, there are three types of specialized relationships: child of, depends on, and links to. A child of relationship expresses hierarchies such as the relationship between projects and subprojects. The depends on relationship shows that a resource has to be seen in the context of another. The links to relationship is for linking resources which can exist independently from each other. Based on the well-defined semantics, the relationship between resources become clear. With the SRADI concept, we provide a holistic view over all information resources across functions and locations, facilitate data provisioning, and enable data-driven decision-making. The distributed digital twin handles the distributed nature of resources over different stakeholders and platforms while providing a basis for integrating both pre-existing historical and real-time information for physical things such as landscape objects. In order to complete the distributed digital twin of the agricultural ecosystem, our future research will focus on linking the calculation and simulation models of the stakeholders with the SRADI. Additional research will also be required regarding enhancing the data security and privacy, as well as developing a federated access management strategy for the SRADI.